And we are back, and you're probably all using grep on a daily basis. It's probably one of the most used and maybe even abused tools. And so I'm very excited to listen to the talk by Dr. Robert van Engelen about the new fast and fuzzy grep.
Hello, my name is Robert van Engelen. I'm with Genevia Incorporated. I've been a professor for 20 years and a computer scientist at the moment at Genevia Incorporated. I'm presenting Ugrep, a high-performance file searching utility. And I want to share with you a couple of algorithms that we worked on that are new as far as we can tell. We did a search and yeah, this is what it is. So I'm going to talk a little bit about Ugrep, in which these algorithms are implemented. Then in depth, we will talk about the new multi-string matching algorithms and the results, and we'll give a brief demo on how this in practice works. You can use this tool to aggressively look for anything, anywhere in your file system. And of course, other grep tools do the same thing, but we added a bunch of new features that makes this, by the users at least, a preferred utility. So Ugrep is relatively new. It's about 18 months old, and a lot of our development happened over the last couple of months. It has an interactive user interface, as you can see here on the top right. It is backwards compatible with Ugrep, so you can basically use it as a replacement. It has the same features as Ugrep, but more. It's high performance. We use threads, lock-free, work stealing, SIMD techniques, pretty standard, but these are well integrated, and we did some studies to make sure that these work very well, including the algorithm that I'm going to talk about in a moment. You can search archives and compressed files just as fast as with any other tool without unpacking or expanding these archives. The query interface, I'll give a demo of that later. It also supports fuzzy search with a max Levenstein distance, so that the edit distance can be specified to look for approximate matches in anything. You can search for approximate matching in any type of media, any type of file. And binary files and searching hex dumps is also supported. Okay, so let's go to the gist of this work at this moment is on multi-string matching. Classic algorithms in many words in a long text, so think about 100 to 1,000 or tens of thousands of words that we're searching for in a large file. Of course, the poor methods, the poor man's implementation is to compare each word at each position in the text. That's not what we want to do. There are algorithms such as BiTab and Hyperscan. Hyperscan is an implementation of BiTab, but accelerated using SIMD and using essentially BiTab buckets. I'm not going to go into details. There's a lot of literature on this, where you can find more information on that. So the problem is what we're looking at, the algorithm that is to use a grep tool to find a number of words. Here are a couple of words as an example. Don't think that this is limited to these few words. This is working fine for hundreds to thousands or tens of thousands of words. So we're looking for a match in the sentence below. The quick brown fox jumps over the lazy dog. And as you can see, we find 5 matches, 3-letter words, as well as 1-letter words. Now, the problem with BiTab in particular is that BiTab can only search quickly for words that are long. Don't get me wrong here. What I mean by that is just that the size of the sliding window that BiTab uses is limited to the shortest word among the words that you're looking for. So in this case would be 1, the shortest word, or 2 short words as A and I, they're both of a length of 1. So the window size that BiTab uses is fairly short. With Hyperscan, you can make buckets of these, so there's some way to get around it, but as long as we are looking for hundreds of thousands of words, then Hyperscan is not going to help much. So we predict a possible match. This is the idea, just like BiTab, predict a possible match by sliding a window over the input. If the sliding window is of a certain size, we can check for the offsets of the window, as offset 0, 1, and 2. And any character at that offset, think about the first character, offset 0, must match at least one of the words, like one of the first characters of all the words that we're looking for. But we don't want this limitation that the offset distance that we can use with the sliding window is limited to the shortest word length. That will be useless, like in this example, when the shortest word is just one character. So here's the example again, where we added the offsets of each of the words, starting with offset 0. As you can see, there are 5 matches in the text below, and the offsets are indicated. So a match of the word the has a t at offset 0, an h at offset 1, and an e at offset 2. That corresponds to the offset information that we have. So the offset information is a approximate word match, because a word that doesn't start with T, like for example, so at offset 0, you can have different letters essentially. We'll come back to some other examples later on. But of course, it's an approximate match, so we still have to deal with false positives, just like BiTAP. For example, if we have the same set of words, and we look for matches in this particular text, we will find two, TO, to be a match, because the first letter can be a T, the second letter can be an O, and that's a false positive, because this is not the word that we're looking for. It's not assuming it's not part of the set of words that we initiated this search with. But this inaccuracy is well known with BiTAP. We can improve this with hashing. The same thing happens with Hyperscan, where they use a hashing method to combine 2 or more characters into one and match those characters. So the false positive rate will drop significantly using that technique. And we will also consider and have implemented hashing with our technique. But the key idea is that BiTAP and the Hyperscan buckets don't work well if the size, if one of the words has a size that's very small, or if a couple of words have a size that are very small, like 1, 2, or 3 characters, because the sliding window is limited to the smallest, the shortest word that we're looking for. And here's the idea that we investigated, and this is an idea that it's new, because there's no other method that we can find in literature that does exactly this. And it's like the puzzle pieces falling together in the right way to optimize this type of search using an arithmetic method. It's an arithmetic method. To understand what's happening, allow me to go through this example, a matching technique using a window size of 4 bytes. So assuming the window size is 4 bytes, you define 2 functions. The first one is match bit, the second one is accept bit. Match bit says that the character C at offset K is 1, is true, if there's a word that has a character at offset K that matches, right? So pretty simple. There's a match if any of the words at that offset has a match. Again, there's no correlation between the characters. It's just a simple check. Accept bit is the same as match bit, but it's only true if any word ends at K with character C. So for example, if we have the word the, and then the letter E, the last letter, at offset 2 is the last letter of the. So we don't care what comes after the, because we have a potential match, right? Okay, so now with these 2 functions, we can use them to predict a match, right? So we read 4 characters at a sliding window, a window size of 4. And if the first character in the sliding window has a accept bit for that character at offset 0, then we have a match. Think about the word A, right? So that's a short word, 1 letter. That's a match. We don't have to look any further. So the accept bit for the letter A at offset 0 is 1. If it's something else, like do, then that's not a match. So then we check if the match bit for D at offset 0 is true. If that's the case, then we still have to check the next letter. So if the next letter has an accept bit of O at offset 0, then the predict match is true, and so on and so forth. So it's basically a recursive breakdown of this problem. You first check if the character we're looking at that offset is the last character of any word, then you stop. If not, if it's a matching character of any word, then we have to check the next character, and so on and so forth. Of course, there's a limit to how far you want to go, and in this case, it's a sliding window of 4 bytes. Now, as you can see in the previous example, we had a lot of logic, that is branching behavior that would normally not be advantageous to accelerate this search. So we want to get away from any branching behavior that that the CPU has to execute, because since branch prediction is known to be pretty bad, in particular for this kind of problem where there's a lot of noise, a lot of randomness in how the branches behave in practice. So the trick now is to use an encoding that will get rid of all the branches, and I'll show you how. We encode the accept bit and match bit information just using 8 bits. That is, since the sliding window is a size 4, we only need 2 bits, and we use 2 bits for accept bit and then match bit to combine all 4 pairs together into 7 bits. So bit 7 is the logical inverse. And it's important, this only works and more efficiently if we use the inverse. As I'll explain and we'll see later and how this works, is to get the inverse of accept bit of the first character at offset 0. Bit 6 is the match bit of character 0 of the character 0. The first character in the sliding window at offset 0, and so on and so forth. There's a very particular reason why we choose this order, not with bit 0 to 7, because this doesn't work in any other way as explained over here. All right, so with this simple encoding, when we get the information from accept bit and match bit, to put that information into a bit vector of 8 bits using inverted logic, as shown here in light blue, that's the part where we compute the 7 bits. The last bit is irrelevant, we essentially have 7 bits. You only need to compare those bits, right? So we compare bit 7 to 0, then we have a predict match. Keep in mind that this is inverted logic. All right, so an accept is a predict match true. If there's a match, we can continue checking the next character in the input as indicated by bit 5 to determine that the predict match is true, and so on and so forth. All right, so this doesn't look like a gain. What did we gain here? It's the same branching behavior is there. We just use a bit vector instead of, these two functions. Well, the point is that once we figure out that this is a branching behavior that can be simulated in logic, using logical operations without any branches, we can accelerate this. We can accelerate this because the branches are expensive and the logical operations are inexpensive. There are like the few of these per window necessary to get to the conclusion whether it is a possible match or there's no match whatsoever. And not knowing that there is no match whatsoever is the most important part of searching. We don't expect matches to be all over the place, right? So ignoring non-matching windows is the key. All right, so this can be simplified. We have no longer branches. We extract the information of the 4 characters from a piece of memory that encodes the accept bit and match bit information that's pre-computed. So we combine this into 7 bits using 2 bits for each of those memory accesses in this particular order to follow the 7 bits to 0 bits. The only thing that you need to do is to compute the bit shifts and OR them together. Compare that to 127, 7F hexadecimal. That is the 7 bits that we're interested in. If that's not 7F, then we have a potential match. If this is equal to 7F, there's guaranteed no match whatsoever. And this is the clever thing. This only requires some arithmetic to compute whether there is or isn't a match. Just like BiTAP. BiTAP is fast because of shifting and bit ORs. This is a fast method to determine if there's a match among thousands of words of any length. One length, words of length 1 can be included, while BiTab cannot. So the proof, to understand how this works, the proof of this method is more visual. I'll spare you the lemmas and theorems necessary to prove this, but it's very clear from this particular viewpoint when we use the bit patterns as a matrix, right? So we have our bit shift by 6, 4, 2, and 1, as shown over here, and we form this matrix. The numbers here are the bit positions, right? So after shifting bits by 6, you have bit 7 and bit 6 all the way to the right, right? And if you shift just by 1, then 7, 6, 5, 4, 3, 2, 1 is remaining. This is a 0 bit that's shifted in. There's a dash here because it's irrelevant, as we'll see later on. But this shifting can then be used, this alignment and the shifting can then be used in the resulting matrix that you see over here to look for columns that we basically have encoded the information column-wise in this matrix, so such that if all of the bits in a column are 0, then we have a match. If any one is still 1, there cannot be a match. And this has to be true, of course, for all columns. But only 4 columns are relevant. The other columns at even offsets are essentially replicants of the previous cases. So if we look carefully at the last column, 6, 4, 2, 1, right, where all these bits are 0, then we have a predicted match corresponds. So let me go back to the branching behavior that we had previously. So 6, 4, 2, 1 says that there's a predicted match if these are all 0. So there's a one-to-one correspondence between this branching behavior with nested if-then else's, and let me go back to the matrix, the column encoding of these bits, these bit values in this matrix. And the 4 cases, because the 4 characters per sliding window. All right. Okay, so that's the key, and this only works. It's important. This only works if the shifts are and only works if the bit locations are pre-computed in the way that is explained in the set of slides. If you try to move the bits, the bits in the bits vector from the start to the end, you have to perform more operations, more work to get this done. It's not impossible, but it's not cheap. This is very cheap, right? So you shift 4 times, 3 ORs, that's it. Compare it to 127, the hexadecimal value is 7F, and that's it. There's a slight small gain here if we don't shift the last by 1, and we change this to shifting 5, 3, 1, 0. And then we get the formula down here on the bottom that saves just 1 instruction. Okay, but that's in the grand scheme of things, just a tiny, tiny gain. But the key is here, a few bit shifts, a few ORs will get you exactly the same as the nested if-then else behavior of bit testing or except bit and match bit testing. All right, so the key is to pre-compute this memory piece, that is the encoding of accept bit and match bit information. Since we have 4 characters and we need 2 bits per character, 1 for accept bit and 1 for match bit, we can put those 2 bits for the 4 cases into 8 bits total and use this same type of encoding in memory. So the memory cell for C2 uses the top 2 bits to encode accept and match bit. The memory cell for the next character uses the next 2 bits, and so on and so forth. And again, this only works if this is encoded in this particular way. So the preprocessing step is essentially to take the collection of words that we are looking for, pre-compute them, scan over them to populate this memory array. And that's actually a lot cheaper. It's fairly cheap because it's just traversing all the words together. Well, if there are lots, and you still have to, of course, traverse them. But during the matching, none of that is relevant, right? For the prediction, none of that is relevant. Once you have a prediction, you still have to check if the prediction is correct, right? This is what all these methods do, because it's a approximate, like BiTAP and Hyperscan, an approximate match. You still have to check if the word actually matches. But that's then cheap, because we ignore everything else and we just get straight to the point where we can perform that match. So the memory part of this for pre-computing is that for a particular window size, in our example is 4, shown here on the top, and so an alphabet size, we assign a memory cell of 0, 1, 2, or 3. These are the 2 bits that we need to store, right? And where the even values mean the match bit is 1. And if the values are less than 2, that means the accept bit is 1. So both are encoded in a particular way. Since we have no matches in the beginning, we have to set both bits because of inverter logic, right? Okay, so let me then show you how we learn a word. We learn a word by updating the memory, this memory cell, this set of cells. Only, of course, if the word is non-zero. Length, right? So we take the minimum, can't look beyond the window size. There's no point in doing so. So m is the minimum of the 2. Then we set our match bit information, right? So from 0 to n minus 2, we exclude the last character. We can set the match bit information in this piece of memory, and that's just by storing 2 zeros, because both match bit is true. Then we the match bit is true, the accept bit we don't touch. So we AND this with 2. The accept bit is, of course, 0, again, the inverted logic, for the last character. So that's what the last statement performs. All right. So since we can pre-process all words using this learning technique, and you can do the matching very efficiently over a long piece of text using, by matching 1,000 words into prediction, how can we improve the prediction rate, that is the acceptance, is to use hashing. This slide just shows that predict match with the example showed it's just for a window size of 4. This of course works for any window size. You can go to whatever window size you want, but of course the window size gets larger. You have to perform more calculations. But that does not necessarily improve the matching capabilities. If you have lots of short words, there's no point in having a large window size. So a sliding window size of 4 seems to be rather optimal as tests and examples and evaluation turned out to be. So the hashing is to combine 2 or more characters into one, just like BiTAP and Hyperscan does. And this works very well with this technique. There's no limitation on what you can do in terms of improving the acceptance rate, that is, limit the number of false positives. And we did a lot of testing, of course, to evaluate different hashing functions and hash sizes. And it turns out that a hash size of 12 works well. So about 12 bits, that is, 12 bits. So we have a couple of kilobytes of memory to feed into the matching algorithm. That's it. It's just a couple of kilobytes. 4 kilobytes works well, which is for 12 bits, or 8 kilobytes, 13. But you don't want to go too large, because if you use regular expressions to feed as words into this engine, then all these combinations of words with those hashes will add up in your pre-analysis. So we picked 4K, that is 12 bits, as beating anything that's currently out there without having to go higher. As you go much higher, the pre-processing overhead becomes larger. So it's a trade-off between pre-processing and matching, essentially. Okay, so this, what's on this slide here, it's just doesn't really show a lot of details that I talked about, and but it's, looking at numbers, looking at 100 words, 1,000 words, different hashing functions, different sizes. What we want to do is beat anything that's out there. One other thing you can do, even though hashing will decrease the false positive rate, is to even implement this in hardware, directly in hardware. There's no software necessary to do the same thing because the algorithm is actually very simple. It's just shifting and ORing, right? So given a window size of 4, you can develop a fuzzy match logic device in hardware, for this case to match the word AB as an approximate match. We don't care about XK, but AB is matched, even the window size is 4, using this technique. So here is the implementation hardware. As you notice, there are 4 memory cells here in this row. The input data is shown here on the top. You can have this optional hashing to improve the false positive rate, right? But then after this memory lookup, you only have 2 bits. So each of the memory cells produces 2 bits, the accept bit and the match bit, with the real logic. Now we can then perform the bit shift by adding these diagonal lines and then ORing them, ORing this information together in a final big NAND to predict whether or not there's a match. Works exactly the same as the software, but of course expected to be much faster. Learning this piece of memory is important because the hardware has to be pre-fed with all the words you're looking for. And this is fairly simple. You only need to add 3 control lines and then memory set like chip select and read write operation to perform this task. Like learning AB is just by using 3 control lines, and that will feed that information into memory and update the memory, just like the software version, but of course, quite expedient. So here's an example run of tests with a software version of this, right? So we have, and just one of our tests, we have 1,000 words of length 1 or longer. So this includes short words like A and I and so on. 1,000 words of 2 or longer. All of these words are extracted from this 100 megabyte text file, which is Wikipedia file that we want to search for these 1,000 words. So for 1 word or longer, 1 character or longer, 2 characters longer, 3 characters longer, 4 characters longer, or 8 characters or longer, as illustrated here in our columns. This is the wall clock elapsed time of an implementation of this algorithm Ugrep compared to Hyperscan, compared to regex, and compared to GNU grep. So for words of 1 character or longer, they get about the same time as for 2 characters or longer, and so on and so forth. The best time is for 8 characters or longer, and that's because basically the algorithm and the predict match algorithm, its window size is fully utilized, right? There's nothing, I mean, there's all words are longer than 4. There's still a bit of a difference between 4 and 8, but that's because of the accuracy of the hashing algorithm that we have, well, longer words to match. It's sort of surprising. There's of course trade-off. If we had only a few words to search, then our methods would probably not be better. But if we go to hundreds, thousands, or tens of thousands of words, then the existing techniques like BiTab, Hyperscan, graphs are another way to represent this, will be slower. So I'll show you a quick demo of the Ugrep tool that has this implementation. The Ugrep tool is publicly available, it's open source, it's been developed for the last couple of months, and it's stable. We will add more features, of course, over time. So it's a bit of work in progress, but it's stable and works great. So Ugrep is also abbreviated UG, and it has a query interface. And what we're going to do is search for all the C++ files in the current directory as shown over here. So the interactive feature of this is pretty neat, we think, because it allows you to navigate directories and zoom into things that you're looking for. So if I type in example, it will show you that these 2 files contain that particular word. You can then zoom into one file by typing tab. This is a file looking for that. And so after finding some matches, you can look for other matches and get that information. Then you can produce all the output by either selecting files, selecting lines, and then quit that will show you the lines that you selected. So it works the same way as grep, essentially allows you to navigate files, set options, produce output, and all the kind of neat things you'd expect in a modern tool. So let me wrap this up and state something about future work. We look into SIMD to vectorize this predict match, either vectorize the computation itself, but it's kind of tricky and probably doesn't scale well, or compute 4 predict match values simultaneously at the offsets 0 to 3. And that will accelerate the sliding window strides because we can just move by 4 instead of by 1. You can find the Ugrep repo and documentation on GitHub. We also add documentation sometime soon about this tool at ugrep.org. And it's also based on the reflex library, repo and documentation. Reflex is a fast regular expression engine because after predicting a match, we still need to verify that it's a match. We use the reflex library to perform this particular task. So thank you for your attention, and let me know if you have any questions. Thanks so much.
Thank you so much, Dr. Van Engelen. It was fascinating. I really love this combination of hardware and software and how it fits together. We've had a previous on the previous summit, we had a talk from Daniel Lemire. He was talking about his work on using SIMD to speed up encodings and other things. So it's a fascination of mine. So I hope everyone else also enjoyed it as much as I did. So let me just quickly check if there are any questions. I'd like to remind that everyone is very welcome to ask questions on our dedicated Slack channel. So far, I do not see any. So I'll just go ahead and ask my question then. So since you mentioned a lot of interesting things on both algorithm optimization and hardware, you know, there are basically two camps in performance. Some are focused on mechanical sympathy, so just try to squeeze out the every bit of performance from the hardware, which is great, and that's your work on SIMD instruction is going to shine. But there is also a camp that is more theoretical. So basically, like, you know, on improving algorithms. So what would be your advice to engineers who start in performance space in terms of which camp is better? And obviously, I expect that there is going to be some sort of hybrid approach. So I'm just curious to hear your thoughts on this.
Yeah, thank you, Taras. And thank you so much for inviting me to this event. I'm honored to be here and help you guys out with any questions and things I can share. So since I have taught high-performance computing for several years at the university, one of the advice that I give to my students is that you cannot really expect to highly optimize a bad algorithm, right? So if an algorithm is already pretty bad in terms of performance, throwing more threads to it or trying SIMD is probably not the best avenue to get high performance. Now, of course, you can argue, like, what is a bad algorithm? I mean, do bad algorithms exist? I can tell, but sometimes algorithms are very tunable, amenable to optimization, and others not. As a matter of fact, you will probably see that parallelizing an algorithm that already runs slow gives you very good scalability, which is counterproductive what you normally expect. Those algorithms already squeeze good performance out of single processors, you know, perform very well in single processors, actually even harder to optimize in parallel threads. So there are, of course, the camps that move in the direction of parallel threads and those that want to do more SIMD-like things. And the best combination is to use, of course, both in that sense. Now, for engineers, I think it's you learn more if you look at existing algorithms and try to optimize them for SIMD or parallelism. I mean, there's a lot of experimentation you can do to gain more insight on what's going on. Assuming that you have the best tools to actually extract more performance information from that, like hardware counter profilers. Hardware counter profilers give you more accurate details instead of instrumentation. And those give you more insight. Now, finding a new algorithm is really tricky. I mean, there has to be a bit of luck. I mean, you can't promise yourself, oh, I'm going to improve or find a new way of doing this, for example, like string matching. It's somewhat like, as inventors say, it just comes overnight when you had a good thought about it. Sometimes with a drink or whatever, a good some social event, you talk about it, and all of a sudden it's like, hey, that's the way we want to do this. And of course, there's a lot of false leads as well. Like you think you found a way of doing things, and experimentation doesn't lead to anything, and nobody publishes any negative results, right? So you won't find any papers saying, "Oh, this was a bad idea." So expect to encounter situations where you think you have a good idea, and it doesn't work out so well as you thought. And I could give you another example of a practical experimentation that went horribly wrong. Another anecdotal story I tell to my students in the past is basically, this was like in the 80s, when basically compilers are getting better at optimizing things for you. And they did so aggressively that in one experiment, the time that you've got is just fantastic. Like, wow, it takes 1 second for this algorithm to run, on this machine. And you basically, I'll tell you what happened, but basically you should always mistrust the machines and verify what's actually happening. And what I mean by that is that you throw in additional code to dump out results, either by checkpointing or making sure that the calculation you perform is actually there. Because compilers are so highly optimized these days that if you perform a loop operation, for example, a timing loop, you time beginning and end of the loop, that if the results of that loop are actually not used further down in your code, the loop is totally gone. It will be optimized away because the compiler has detected there's no output dependence. So be very wary about this compiler optimization, showing that your code runs very fast. If all you're doing is just running some code that's timed in a loop, and maybe the compiler just optimized everything away. And then you have, of course, the sort of like a Heisenberg type problem. Like if you want to add instrumentation, or you want to add timing events, that will change your code too. And it can affect also compiler optimizations. And it's not always well understood what is happening precisely, because the compiler is still a bit of a black box. That's improving. We see more compiler technology being developed where you can actually see what the compiler produces. For example, Compiler Explorer is an online project. It's great to understand what the compiler spits out as assembly code for different machines. So highly recommended at Compiler Explorer online to figure out what compilers actually do. So yeah, I'm in both camps. Theory is interesting, but you got to be a bit lucky and hard work to find out, if there's an opportunity to find a new algorithm. But you learn a lot from existing code that people have worked on and trying to optimize this further or change it from one type of SIMD instruction to another, right? We have new processors coming about that like ARM-based processors. They're not really new, but they're going to be more popular, and they have a different SIMD instruction set. So yeah, I'm not sure if that answers your question, but
yeah, it does. It's a lot of wisdom here. It's just, so first of all, like writing benchmarks is extremely hard. That's why there are very specialized things like for Java, there's JMH and all these. Compiler Explorer is an amazing tool, definitely, but unfortunately it doesn't work so much for managed languages, because in managed languages there is JIT also that can change the code online. So it's there is a lot of trickiness everywhere involved. So benchmarking is very hard. So yeah, it's the other thing is, you mentioned that the algorithms, there are like experiments and failed experiments, and it seems like I would probably even add that it's not always a reason to be discouraged when your experiments are not looking very promising for the use case that you're trying to apply them to, because a lot of the algorithms these days are just hybrid approaches. Like, for example, introsort, which is used as a default sorting algorithm for C++, it's just a hybrid of a bunch of different sorts. And in fact, it's very common when almost every sorting algorithm that is super advanced benefits from using something like insertion sort for very small chunks,
yes.
just because it has lower overhead. So I'm actually even curious if you have found something like that, like some hybrid approach for string matching useful. Like, do you combine multiple different techniques, or maybe different
Mhm.
encodings or different sizes of the input?
Yeah, so of course, Ugrep is an example of the algorithm that we worked on, that I mostly worked on for the last couple of months. But it's true that if you are searching just a few words, let's say 4, then this multi-string matching algorithm may not be the best. It's just like, it's probably better to use hyperscan, like bitap, bytap buckets in that sense. So yeah, there will always be thresholds where you can check, oh, this search query type is better suited using this method, and otherwise other methods. And it's exactly like you point out, sorting. Insertion sort works great unless you have like thousands of elements in your array. The tricky thing, however, is you don't know if that's true for all machines that you're dealing with. Right. So,
Right.
and it depends a lot on memory hierarchy, typically. Branch prediction, whether it's implemented or not, whether you have certain simpler processes or not. So you have to make certain assumptions. And easily that type of benchmarking can take days, to accumulate of all these machines. I'm not entirely sure if it's worthwhile, but if you have a real-time problem where you have to solve something within those limits, then you just want to optimize for that particular machine that you have in mind. And there's also a technique called auto-tuning that's used in numerical libraries like BLAS, the Atlas system, for example. So basically what it does is runs numerical solvers, different types, on the machine that you have. And it gives you a parameterization of the library. Well, we'll basically recompile a library using those parameters, and gives you the best performance that it could predict. It's not, like I say, the best performance, not perhaps optimal. Striving for the optimal is like, is really difficult. I wouldn't say NP hard or something, but it's almost like the decidability problem. So yeah, there's auto tuning, and I've thought about auto tuning for this, but maybe it's a bit of an overkill. It would be great, but it depends so much on the type of strings you're looking for anyway. So it will be pretty difficult to always guarantee optimal performance in general for all types of machines. But yeah, auto tuning is another way of addressing what you're pointing out.
So basically, measure all the time and do not rely on any magical silver bullets because they are all specific. And in fact, in our next talk, Stratus is going to talk about some AI, or I guess automatic tuning techniques to select the most appropriate algorithm. So I think it's going to be a good continuation of this talk. Thank you so much again for taking time to attend the summit. It's been an immense pleasure and honor to having you. And have a wonderful day.